I think there's somebody stuck in a waiting room though, so I hope they're good. But we're gonna be going over image classification and machine learning. So if you guys remember from the last time we went over like the brief overview of machine learning, but we're gonna dive a bit deeper. But first, we're gonna talk about some like terminology. So these are like words and phrases that are gonna be commonly used when like talking about machine learning. So the first thing is a label. So a label is like a trait that we want to predict. So an example is like if an email is spam or not spam. So basically what this means is like, for example, in your Gmail, right? It like auto detects if an email is spam or not spam. And the label is spam or not spam because that's what you're detecting. And then features are input variables. So a simple project might use like one feature, while more advanced, sophisticated projects could use millions of features. So an example of feature inside our spam detector example, it'd be like the words inside your email, the sender's address, the time of the email, and like whether the email contains like certain phrases, right? So all of those are like red flags that might mean like, hey, this email is probably going to be spam. So those are the different types of features. And then examples. So an example is like an instance of data. So there are two different types of categories. The first one is labeled examples. Labeled examples, it includes both the feature and the label, and it's used to train the model. So in our spam detector example, emails that the user have explicitly marked as spam or not spam, those are labeled examples. The reason why they're labeled is because we already know that, hey, this email is spam, right? Or this one isn't. So they're already marked. And unlabeled examples are the same thing. It contains features. However, it doesn't contain the label. So those are like emails that are not marked yet, and they're like new emails that users haven't yet labeled. And we use the machine learning model to predict the label on these unlabeled examples. So that'll make a bit more sense later if it's confusing. But so the last thing is what a model is. So a model is basically like your algorithm, and it defines the relationships between features and labels. So there are two phases inside a model's life. The first one is training. So that's where you're creating or learning the model. So like you show the model the labeled examples and you let it gradually learn like the relationships between features and labels. And the second phase is inference, which is basically applying your already trained model to unlabeled examples. So you see the trained model to predict the label. You use the trained model to predict the label. So all of that stuff that we just went over, you can find that on Google's machine learning crash course. They offer like a pretty in-depth crash course, and it's down here in the bottom left. But basically, it's pretty important just to like some of those key terms. But anyways, now we're going to start about image classification. So these slides are actually taken from Stanford's computer vision course from 2017. They're all online. We have like links to like their lectures on YouTube and their slides too. But basically, they're pretty good and they're pretty useful. And I thought like there wasn't any point in creating new slides because like it's hard to compete against Stanford's. So we're just gonna kind of borrow these. If there are any questions, you guys can always let us know. But basically, to deal with images, the computer is given right like an image. So they're given an image and they need to somehow tell that this image is a cat, right? And so what commonly is used when like training your machine learning model with images is you have a set of discrete labels. For example, it could be four of them, like dog, cat, truck, and plane. And then if you're given an image, you want your machine learning model to say like, this is 100% a cat, 0% a dog, 0% a truck, 0% a plane, right? That'd be very accurate. That'd be basically perfect. However, if you're given an image that's like a dog slash cat mix or something, then it might give different numbers, like maybe 50% dog, 50% cat, 0% truck, 0% plane. Obviously, your model is not going to be like as accurate, but that's like what one of your end results wants to look like. But there's a problem, which is known as like the semantic gap. The word semantic, it just talks about images. It's basically like another word for images and illustrations. Semantic gap basically means like issues with labeling images, right? And it's commonly used, but basically all you need to know is that because you're given an image, the computer can't see what we see, right? The only thing the computer gets is your image file. And from your image file, there are some properties they can get, right? Which is the length and width, right? The dimensions of your image, as well as the pixels of your images. And pixels are just RGB colors, right? They're just colors basically. So that's why your computer sees something like this matrix here, right? And all of these numbers are all RGB values, right, from 0 to 255. And normally it's a 3D matrix, which is width by length or height, width, whatever dimensions, and then times 3, because there are 3 channels, which stands for the RGB values. And then, so given these numbers, you need to somehow build a model, right, that the computer can look at these numbers and say, hey, that's a cat, right? Or hey, that's a dog. But there are some more issues, which is the first one is viewpoint variation. So if your camera is like from the left side and taking a picture of this cat, you might get a set of numbers that look like this. However, if your camera moves, for example, like 90 degrees to the right, you're gonna get a totally different picture with all different pixels, all different numbers. However, it's still a cat. So you need to somehow account for something like that. And also illumination, right? Same thought process. If the lighting is different, all of your pixels are going to be different once again. However, the picture is still a cat. And there's also deformation, right? So if they don't exactly look like cats, occlusion, which is basically if it's hidden, right? So for example, the one on the right is pretty seriously hidden. We can tell it's still a cat. We see this tail, we see a little hump underneath the cushion, but your machine learning picture doesn't know that. It just gets all of the pixels. And then background clutter, right? So these cats are blending in with their respective backgrounds, orange background, some snow here. And then lastly is intra-class variation, which is basically like different species of cats, right? Or different sizes, different shapes, or kittens, right? Which are baby cats, same thing. And so those are all problems. So if you aren't like familiar with machine learning, you might like try making an image classifier, which basically has like a little function here, right? So it takes in def class image, right? It takes in an image, then it does some magic and returns a class label. But then you're gonna realize that there's no way you can hard code some magic and return your class label. It's not like sorting a list of numbers where there is a way to actually figure out how to give a definite result. There's no obvious way to hard code the algorithm for recognizing a cat. And the same goes for all other like images. However, there have been like some attempts. So the first one, like this one, is finding the edges. After you find edges, you want to find like corners, right? Because corners are pretty defining. So for example, you might go like, if you find 3 different lines that intersect at one point, that's probably a corner. And like cat ears have like 3 corners here on each side. However, there's like 2 main problems. The first one is it's not really accurate, right? All of the challenges we talked about earlier like still apply. Like how do you know if you can only see a tail? And then also the second thing is it's not very robust, which when we say robust, we mean like you can't duplicate it for like another image. For example, if I want to start classifying dogs instead of cats, I have to redo all of my rules. All of these corner rules that apply to cats might not apply to dogs because it's like a whole different species. So what you need to do is you need to use some machine learning. We're gonna watch this like really short video. It's also from Google and it's talking about how they classify images.
The internet wouldn't be the same without cats. From Garfield to Lil Bub and GitHub's Octocat, cats have become the internet's unofficial mascot, playing critical roles in some of the web's most viral content. But cats are unpredictable creatures. With millions upon millions of cat photos on the web, each containing very different shapes, textures, colors, poses, and backgrounds, how do we determine whether an image has a cat in it? Google Photos organizes all of your photos and makes them searchable. But how are cat photos identified when they are merely labeled with nondescript terms like Max? Image classification assigns text labels to images. But even with a huge number of training examples, Computers cannot extrapolate enough meaningful information from raw pixels alone to easily identify a cat in a photo. We need to build models that can see pictures more like humans do. We can do that with a convolutional neural network. A convolutional filter is an n by n, for example, 3 by 3 grid of numbers that is applied to an image in different ways to generate a feature map, a map of all feature crosses or combinations in the image. Filters form a feature hierarchy. ConvNets use filters to build representations that become progressively easier to classify, from pixels to textures, from textures to shapes, and from shapes to objects. Training a small ConvNet, we can build a cat classifier that can identify cats with up to 80% accuracy using just 40 lines of code. Let's see the image classifier in action. Is there a cat in this photo? Definitely. How about this one? Most certainly not. A drawing of a cat is still identified as a cat. So is a cat relaxing on a bed. But a cat in a bunny-shaped cat bed? Not so much. However, even despite its high accuracy, the ConvNet has its limitations. As you can see, the human eye is still better than a machine at cat classification. Using a similar technique to the cat classifier, we can train models to classify dogs or even inanimate objects like handbags. To identify content labels in our training data, we leverage the same Google machine learning technology that powers Google Image Search and Google Photos, which can recognize over 27,000 different labels. ConvNets can also be trained to recognize more abstract concepts, such as whether a photo was taken on a smartphone or by a professional. These nets can be built on top of a pre-trained-based network via a process called transfer learning, which makes it possible to train on far less data. Keep reading to learn more about convolutional neural networks.
So that was basically the whole video. So hopefully that made sense. The most important part was like the convolutional neural network. The parts at the end about like the transfer learning aren't as important, but the main goal from that video is that basically with all of these images, it's way too hard to get stuff just by the little pixels. So they need to have some sort of filter that has like a wider like angle lens basically, so they can see images more like we can. And so that's basically it for this theory portion. Um, uh, these are like some of the credits resources. We'll share them later. But now I'm gonna stop sharing. I think Senkai is gonna take over and he's gonna continue.
Give me a second. Okay, so yeah, so the video talked about convolutional neural networks, and today we're gonna do a demo. We did it like before the spring break, but that wasn't as thorough because I didn't really explain all that much. And today we're gonna basically go over it again, but it's not the same one. We're using a different data set. This time we're still classifying images, but we have like more classes. So airplanes, blah, 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 trucks, cats. And yeah, so we'll be using Keras. It's a part of TensorFlow. And we will also be using Matplot to show the pictures. Yeah, why don't we get started? So this is Google Collab, this website. So this is a place to run Jupyter notebooks and on Google servers so that you don't have to install anything and you don't have to buy GPUs and stuff. And yeah, so just going to run this code block and just wait for it to boot up. Okay, it's initializing. Okay. Yeah. So the number here shows that it's been run before. And let's download the dataset. So a dataset is a large group of usually labeled examples used to train models. And we're going to download them. And we're going to split them into the training data set and then the testing data set. So usually when we have a data set, we don't use all of the data for training because when we do that, we might not know when the model overfit or underfit. So overfit, underfit looks like this. So yeah. So imagine all of these dots are individual like images, and maybe the bottom is something other than time, maybe type or something, and then just don't worry about that. But so basically, when you underfit, you kind of the model doesn't really capture the pattern, and when it overfit, it cares about the data too much that it tries to like aggressively match what's showing the data. But when we have a good fit, then we kind of approximate the pattern, and yeah, that's what you want. So in order to know that we are not overfitting or underfitting, we have to have some kind of testing data set so that we know that we're not screwing it up. So that, yeah. And they already prepared it for us, so we don't technically have to split it ourselves. So yep. And yeah, so actually in for this demo, the test dataset is actually the validation dataset. It is used every epoch. We're gonna explain what it is later, but basically the validation dataset it is used to like evaluate the model at every repetition over the whole dataset, and then we can use it to check how it's improving, and then we'll use the result on the performance of the result of the evaluation to update the hyperparameters of the model, like the learning rates, which is the rate at which the model like is updated based on the algorithm. So yeah, so this is technically the validation data set, and yeah, but it's not used to train the model, just so you know. And technically the test data set should only be used for final evaluation of the model. So you want to see how the model is doing on like real world data. And yeah, because the models have seen the training data set, and technically the validation data set, we should not use them to test the model. And so yeah, this block, we use this block to basically show the data, so don't worry about these too much. Yeah, so as you can see, these are our images. So yeah, and also the reason why we use blurry images is because okay, so the reason why we use blurry images is because if we get high resolution images, the processing power it needs to train the model might be too large to handle. So yeah, and usually these are like enough for us. So yeah, we just go with those. Let's see what else. So okay. So for each example of a data set is like a point on a multidimensional graph, and each feature represent an axis. So think of an example as a dot, as a point on the graph, right? And then each feature is like a coordinate, yeah. So like X and Y stuff, but there's a lot of feature this time because we have, well, technically they're all raw data, so they don't have any feature that's like immediately extractable. That's why we need to use convolutional neural network to extract these features and feed it into a neural network. So yeah, we need the convolution part, and then we attach it to the neural network part, and then the result of it will give us the classification. So oh, by the way, the reason why we divide by 250, we divide on each pixel value by 255 is because we want to normalize the data set. So normalization, we do normalization when we want to scale all the variables down to fit in the same range of numbers. So typically we want to fit it in like from 0 to 1. So this is so that when learning the model, it doesn't take variables that have higher values to be more important. So if we normalize it, the algorithm, the training algorithm, will treat them equally. Yeah. So. And also, usually when we normalize, we do something called we try to achieve something called the zero mean and unit variance. So this is a standard way of normalizing data. For each variable, we will determine the mean of this variable, and then we subtract this mean from all values of this variable across all examples. And so after that, we also determine the standard deviation, and we divide this all the values by this standard deviation. And after that, we will get zero mean unit variance. And this one is not very nasty to handle because we already know what the max value of a pixel is. So we can just divide that to get all of them inside the 0 to 1 range. And yeah, that's that. And okay, let's go. So yeah, this is basically a graph of how like convolutional neural network like works. But before I talk about that, let's talk about what neural network is. Okay, so a neural network is it's like a brain, and each node of a network has multiple inputs. So at least in the hidden layer, each node has multiple inputs. So you get the inputs from so for each node, it accepts input from all nodes of the previous layer. So the previous layer's output is this layer's input. And a node also has its weight and bias. So think mx plus b, but the m and the b and the x are all vectors. A vector is basically a list of numbers, right? So, and yeah, and also has an activation function, and finally it'll produce an output value. So in the first layer, each value is a node, each variable, whatever you want to call it, it's a node. And from the second layer and onwards, each node accepts input, and then it apply the weight and the bias it's got. So it multiplies the input by the weight, and then it adds the bias, and then it gives that to the activation function, and the activation function determines what output this node so we're going to give to the next layer. And yeah, and the activation function is much like a neuron, and it determines how much this neuron wants to light up once you fire the other neurons. Yeah. So. So Keras is great for like small projects because it's easier to construct models like this, like simple models like this using the sequential class. So here, the sequential class. And yeah, so it's basically an array of layers, and it doesn't have to be only neural net. Some can be special, like the convolution layers or pooling or dropouts, etc. Let's go back a bit to the convolution stuff. So basically, so this is the image, right? This is the input, and the input has 3 channels, red, green, and blue. So there's quite a lot of there's a lot of data we have to process. So we want to simplify this data. We want to extract the pattern, we want to extract the feature, and using the convolution and the pooling layer. So the convolution, a convolution layer has a kernel or a filter, and it slides this filter across the image to extract values from it. So the resultant matrix will become the new image, and then it does some pooling. So pooling basically summarize the image and get rid of the unnecessary bits. and it does that again, and then finally it flattens the image into a list of features that the neural network can accept, because yeah, before it's just raw data, and it's too nasty for neural network. That'll be a lot of processing. That'll be a lot of data to process. So that's why we need the convolution stuff. And now it's basically just a classification problem. We just put a bunch of layers, and yeah, here we have the outputs, and we're done with it. So here are some of the layers we've got. These are all the convolution stuff. So each layer, it has a number of it accepts. So for each layer, we specify the number of nodes. The number of nodes in this layer. And for convolution layer, we also need a kernel size. So this is a 3 pixel by 3 pixel kernel or filter. And yeah, and it'll learn, like, so during the training process, it'll learn what kind of filter it needs to like use. And so here's the activation function. So let me show you what the actual activation function actually looks like. ReLU. So as you can see, this is what it looks like. So the reason why it has a weird shape like that is because we want non-linearity. So we don't want a straight line. We want like non-linear functions in our neural graph. So that way, this neural net will be able to like simulate complex functions. So if we have a straight line as our activation function, that is, we don't even have an activation function. We just apply the weight and bias. We will lose non-linearity, and then the whole neural net is like a linear progression, which is useless against more complex data. So yeah. So we have ReLU. That this is a pretty standard activation function, and then we have the shape of the input layer. So for each image is a 32 pixel by 32 pixel image, and then it has 3 channels, RGB. And yeah, so this describes the multidimensional array that we're going to feed into the model. So technically, this is the first layer, and this is the second layer, but it's kind of, I guess they just want it to be simple. So they have a keyword argument here to specify the input shape. And yeah, and so in NumPy or in other like scientific computations libraries, a shape describes the dimensions of an array, and the array can be multidimensional array. So so sometimes we call it 2D array a matrix, and 3D array, I don't know, 3D array probably just a 3D array, I guess. And yeah, and a max pooling layer. This has a kernel too. So a max pooling layer basically assigns the kernel across the image, the same as convolution layer, but the difference is that it for the max pooling layer, it chooses the largest pixel value from this 2x2 region, and it extracts that into the new image, and it ignores the rest. And yeah, so basically repeat it a few times. So this is not a complex task, so we don't really need too many. So that's why I only have like a few convolution layers. For like more complex stuff, like bounding box, drawing a bounding box on certain objects, sometimes they can get even crazier. You might have like dozens of layers in this model, and that's going to take a lot of time to train, but we don't have that, so that's cool. Let's see how they executed that. Oh, and this is what the convolution layer looks like. So this is the kernel, and we multiply the kernel by the actual image, at least a part of the image, and then, for example, so 4 times 0 plus 0 times 0, and so on, and we sum that up and we put it in the new image, and this becomes a single value in the new image. Let's see how we run it. Yeah. Okay, we can use the summary function to, well, to summarize it, I guess. So here are the layers, the shape of its output, and the number of parameters it needs. Yeah, and all of these parameters, or the all of these parameters will be trained during the training process. And the parameters are the weight and the bias, basically. And for the convolution layers, they are the kernel, the values in the kernel. Yeah, sometimes they call these vectors tensors, but they're basically the same thing. And now we're going to add the neural network like after the convolution layers. So in Keras, Keras calls neural network layers dense. So yeah, and in this layer we're going to have 64 nodes, and we're still going to use ReLU, and then the last layer we're going to use 10 nodes, and yeah, and the last layer is basically the output. So each of the 10 nodes will describe the probability that this image belongs to a certain class. Yep. And let's compile it. Let's see. So after defining the model, we also have to specify how this model is trained using the compile function. So we're going to start with the loss function first. So a loss function lets the model know how bad it's doing so that it can improve, or it can figure out a way to change the weights and bias using calculus. And so the actual function, I mean the actual thing that changes the weights and bias is the optimizer. And yeah, so it basically does some calculus stuff called gradient descent on the loss function, and then figure out what is the best way to reduce the loss. So let me show you. Gradient descent. So basically, so imagine you currently your model has a high loss against your training data. So gradient descent will analyze where you're at in this loss function, like according to your model parameters and the output and so on. And then it will differentiate the function and get a gradient, and it'll figure out how to go down this slope, yeah, using the gradient. So the gradient is the calculus. Well, the gradient is the slope, but it's it's multidimensional, I guess. So it has like a slope for all of the axes, all of the features in this in an example. So yeah, and so you might want to tell. So you might think that you should tell the algorithm to go as far as possible, but that's actually not a good idea, because what if because what if you've gone too far and gone into like a local minimum, and yeah, wait, actually, yeah. So anyway, you want to take it smoothly, so that's why we have a learning rate to control how much we go down the slope at each iteration of the example. So yeah. So in this case, we don't specify the learning rate because this optimizer handles it for us. Let's see. So the optimizer updates the weight and the bias of each node, and like the good ones, the better ones, improves the efficiency of the training algorithm, and are the training algorithm themselves. So yeah, so the good ones are very efficient, and a basic one, like a stochastic gradient descent, does the job and only uses calculus. But the better ones combine multiple techniques like momentum and to change the learning rate adaptively, and it speeds up the training process and improves accuracy. So, and lastly, we have a metric. So the metrics is basically something that lets you know how well the model is doing. And it's not used in this training process. It's just used to let you know. But because we as humans cannot interpret what the loss actually means in terms of progress. So accuracy is a better metric for that. So yeah, so it'll show like 90% accurate or something like that. So for now, you don't have to worry about what this loss function actually is. But if you're interested, let's see. Let's see if I can. So I'll show you. We're not going to watch this video. We're not going to watch this video because we don't have enough time, and I didn't plan to watch it, show it here. But in case you're curious what this is about, I am just going to send it in the chat. Send it in the chat. You can watch it later. So yeah, after we compile it, we can use it. We can actually train the model on these images, and yeah. And as you can see, the test dataset we created is not actually the test dataset; it's a validation dataset. And yeah, and we're going to train the model on the training images 10 times. We're going to repeat the training process 10 times because we don't have enough. We don't have enough images usually. Well, let me repeat it. Let me rephrase it. So usually we don't have as many images as we want. So so we just basically reuse this training image to like yeah, we basically just reuse the training image, and maybe we will get something out of it. Yeah. And so for each epoch, for each epoch, it's the history is going to tell us at which epoch the algorithm, the accuracy is best. So maybe we can revert to that thing, to that epoch or whatever. And we can just do it. It's pretty quick, but so yeah, unlike last time, this only has 10 epochs and only has like around 1,000 images. So it's pretty quick. Plus, we're running on Google servers. Yeah. Since this is a pretty simple model, we're going to our accuracy might not be the best, but it's actually pretty good considering like how much layers this have and how quick the training process is. So yeah. So based on the results on the training data, we get an accuracy of 79%. However, it's biased because the algorithm already knows the training data. So yeah, it's not an accurate metric. And so in the validation data set, we only get like 70%. So yeah. So don't trust the training data set accuracy. Always give it another real world unbiased data set to evaluate it. So let's plot the graph. Let's plot the accuracy. Yeah, for the training data set, our accuracy slowly improves, and for the validation data set, kind of plateaus at the end. And I believe if we train even further, the model will overfit. The training data set accuracy is still going to increase, but the algorithm is going to overfit, and then the validation data set accuracy is going to decrease. So yeah, that's it for this demo. And Eric, do you have anything to say?
No, yeah, that's basically it. I think we're gonna basically end here. If you guys have any questions, you guys can stay behind. We'll stay for a couple more minutes. Otherwise, we'll see you guys next week. If you guys are interested in learning more about like this stuff, there are a lot of like courses, classes, free resources you guys can find online. Yeah, that's basically it.
Do you guys have any questions? Andrew, Calvin, and Zach? If not, I guess we can just end the meeting.
Yeah, I'm just gonna end the meeting.